Hello, okay, for this section we're going to talk about the special rules that we have for taking the derivative. Up to this point, we've been used to taking the derivative using the limit, the definition of a derivative with the limit and the difference quotient. But that process can be very tedious and can be a convoluted process. So let's look at some ways, or using the derivative rules that we have here, how we can go about trying to take the derivative of particular type of functions. I want to also remind you that there are several notations for derivatives, symbols, and you may have seen them, and depending on which level of calculus you're working in, then that will determine which notation you will see. And of course it all depends on your instructor's choice. But derivative can be symbolized in this way or this way, and that's regarded as the Leibniz notation, or you may see the Lagrange notation, which is the prime, y prime, f prime, s prime, f of x prime, s of t prime, so on and so forth. Or you may see the Euler notation, and of course we can have double primes in these particular cases to denote the second derivative. Likewise here we can have a power of 2 there to denote the second derivative. Here we have the Euler's notation. This denotes the first derivative. This denotes the second derivative. You can also see it with the little dot here on top of the y, and if it has double dot, that's the second derivative. And likewise, these particular notations you'll more or less see in a higher level calculus, or when you start talking about vectors and mechanics and stuff like that, you'll see those type of notations in a high level calculus. This is called a partial derivative, and you'll probably see that a lot in a course called differential equations. But now that we've gotten our derivative notations out of the way, let's go ahead and look at some problems as far as how these rules can be applied here. Alright, the first of our rules is called the constant rule. So the constant rule, we're going to look at that. Let's say if we have, this is our constant rule. Let's say we have a function, f of x is equals to, let's say, 7. To find the derivative of this function right here, if the question is find the derivative of the function, find the derivative of the function. Of the function f of x. Well, to find the derivative, it's just, again, we use the notation, so we're going to use f prime of x. The derivative, which is denoted by this prime symbol, well, the derivative of any constant, if you just have a constant, no variable, the derivative of a constant is just simply 0. So, and you can see that's the first rule here. The derivative of any constant is 0. So we've seen how that rule applies here. Alright, and of course we could use the other notations if we wanted to. Let's say if we have another example, negative 14. The derivative again of any constant is 0. So that's all we need to say in that particular case. So that's our constant rule. Let's look at another rule. Let's say we have the power rule. Power rule is power rule. So let's say if we have a function, and I'm using f of x, I'm going to be using f of x and y. So let's say we have a function of x is equals to, let's say, x to the third power. Then by the power rule, the derivative, f prime of x, which denotes the derivative, is just a matter of taking this power, wrapping it or multiplying it with the coefficient that's out here. So 3 times, it's understood or implied to be 1 here, so 3 times 1 is 3. Write the base and then subtract 1 from the power. 3 minus 1. So this gives me a result of 3x squared. That's what f prime of x is. So it's just a matter of multiplying the power times the coefficient and subtracting 1 from the power. And that's it. So this is f prime of x. So let's say we have another example. This is our first example. Let's say we have another example using the power rule. If we have y is equals to let's say we have x to the negative, let's say 3 power, x to the negative 3 power. Well, now let's go ahead and show this. Since we are using y here, I could either use y prime to denote the derivative, or I can use dy dx. Let's go ahead and use the dy dx notation. So dy dx then will be, again, we're using the power rule, so it's multiplying this power times the coefficient there. So that would be what? A negative 3 times, understood to be 1, so negative 3 times 1, which is negative 3. Putting x, the base here, and I'm also now minus 3, and I'm subtracting 1 from that power that was originally there. Now we just a matter of simplifying, so this is going to be negative 3x, and when we simplify, this becomes negative 4. Now, you know in math, you're not allowed to leave your answer as a negative power, so you want to simplify this. So to simplify this, remember our power rule from earlier algebra. If we have a base raised to a negative power, let's say n, then that's just simplifies to be 1 over the base raised 1 over the base raised to the positive version of that power. So likewise here, this can be regarded as negative 3 times x to the negative 4. We want to convert this part of our problem, so that would be negative 3 times, and using that rule here, this becomes 1 over x to the 4th, which simplifies to be negative 3 over x to the 4th. So that's what our derivative is using the power rule. Alright, let's go ahead and look at some of the other rules. The constant multiple rule. Constant multiple rule is this. It's basically for constant multiple. It's pretty much similar to the power rule. Let's say we have y is equals to 3x squared. You notice I have this 3 here now. What this is basically saying is I can do this. I can say y prime, or dy, let's say dy dx, is just a matter of bringing this 3 out to the front and taking the derivative of the x squared. So bring the 3 out to the front, take the derivative of the x squared. So this would be 3, and then the derivative of this part is just the power rule, 2 times 1, which is 2. So this would be 3 times, this becomes 2. So I'm bringing this power to the coefficient, and then I'm subtracting 1 from the power. So this is 2 minus 1. And then we have, as a result, well, we have products here, so we can multiply these two, so that becomes 6x to the 1. Now, instead of going through all of that, we could have just simply say, okay, well, this gets multiplied by the coefficient here, 2 times 3, and then subtract 1 from the power. 2 times 3 is 6, subtract 1 from the power gives me x to the 1. So you don't necessarily have to go and through that particular process. Just use the same rule we've been using. But just to illustrate the rule, I just wanted to show you what the constant multiple rule stated. Let's go on to some other rules. The sum and difference rule. Sum and difference. Basically, we would use this rule when we have like polynomials. For example, let's say you had f of x is equals to, let's say, x to the 5th plus x to the 4th minus 7x to the 2nd. And let's say plus, let's say 3. Basically the sum, let's go ahead and make this sum. Well, let's leave it as a difference there so that we can illustrate both the sum and difference. All the rule is saying is if you have a sum of functions which composes one big functions, you can take the derivative by just taking the derivative of each component of that sum or difference. So if you want to do f prime of x is simply just looking at this individually right here, and taking the derivative of that. So we have taking the derivative of this means we wrap the power in the front. So 5, and we subtract 1 from the power. 5 minus 1. And then go to this guy, you do the same thing. 4, x4 minus 1. Go to that guy, you do the same thing. X to the 2 minus 1. And of course the derivative of a constant is just going to be, again, 0. So we can just disregard that constant. And then we just go ahead and simplify. This would be 5x to the 4 plus 4x to the 3 minus 7. I'm sorry, this would be 2 times 7, which would give us 14. So we should have had a 14 here. 14 here, x. And that will be your answer. So this just that's all the sum and difference rule is saying. It's saying this: if you have the derivative of the sum of functions, it's just a matter of taking the derivative of each component of that sum. Likewise with the difference. If you have the derivative of a difference of functions, it's just a matter of taking the derivative of each of the components that composes this difference. And you can regard this is the F, that's the G, this is H, that's the S. So you're taking the derivative of each of these individual functions. Alright, so that's the sum and difference rule. Let's go into some more complicated rules. Here, let's go into the product rule. The product rule for the derivative, we can use whenever we have a product. So the product rule is used whenever you have a product, you can take the derivative using the product rule. So let's go ahead and look at an example here. Let's say if we have 2x cubed, 3x minus 5. Let's say this is y is equals to that. Well, according to the product rule, or let's call this f of x. If you want to call this f of x, it doesn't matter. All the product rule is this, and I'm going to show you what it is, and then I'm going to explain the rule to you after I show you. First thing, you have a product here. So if you pretty much look at this function here and say, okay, I'm going to call this one of my factors, because you have to kind of separate it into two factors. So I'm going to call this the first factor, and let me call this the second factor. Second. I'm going to use f for the first factor, and I'm going to use s for the second factor. The product rule says the derivative can be defined by doing this little notation. The first times the derivative of the second plus the second times the derivative of the first. Think of df means derivative of first, ds means derivative of second. It's just a notation. When I was in college, I decided to use that notation just to unconfuse, if that's a word, the rule. So it's the first. The first would be whatever the first factor is. So this becomes 2x cubed times the derivative of the second. So that's times the derivative of the second. Well, this is the second here. So let's look at that function. If we have that as a function, the derivative of that, well, to take the derivative of that, you just need to take the derivative of each term there. So the derivative of each term will be taking the derivative of the 3x, which will be, in this case, 3. Because I'm bringing the power of 1 times the 3. And then I subtract 1 from the power, it becomes 0. X to any power, x to the power of 0 is always 1. In other words, illustrating the rule 3, x, this becomes 3x to the 1 minus 1. I take the 1 and multiply it to the front, so that's 3x to the 1 minus 1, which becomes 3x to the 0. But anything raised to the 0 power is 1, so that's just 3 times 1. So that's just 3 there. Alright, so it's the first, which we have here, times the derivative of the second. The derivative of this is just 3. The derivative of a constant is 0, so that just goes. So that's just all that's the derivative of the second. Plus the second, which is this whole function here, and I'm using brackets as a distinguishing factor. You can use parentheses, but I'm just using brackets rather, to make things less confusing. So second is the 3x minus 5, and that's times the derivative of the first. Well, the first is this. The derivative of that is just the constant multiple and the power rule used together. So this will be 3 times 2. So 3 times 2 is 6, and then I subtract 1 from the power. So this would be times 6x to the 2, because I'm subtracting 1 from the power. And then you just go ahead and simplify. These values can get multiplied together. Through 2 times 3, that's 6, and that's x cubed plus, again, this is a monomial times a binomial, so you can go ahead and distribute this to each term of the binomial. So 6x squared gets distributed to the 3x. That gives me what? 18x cubed, and 6 times 5 gives me what? 30x squared. So that is your result right there when you take the derivative using the product rule. So it's just a matter of doing the first times the derivative of the second plus the second times the derivative of the first. Now if you look over here, the rule says this. The product rule is if you have an f of x function and a g of x function. So what they're doing is they're saying this factor is a function, that factor is a function. So this would be your f of x, that would be your g of x. The derivative of it is just writing the f of x function and multiplying that by the derivative of the g of x function. We wrote the f of x function and we multiply it by the derivative of the g of x function. And then we add the g of x function and multiply that by the derivative of the f of x function. So we add the g of x function and we multiply that by the derivative of the f function, f of x function. And then we just simplify. And that's all there is to the rule. Now you may be looking at this and say, you know what? Why did you use the product rule? You could have used another rule. Let's look at the problem here. 2x cubed times 3x minus 5. Well, as long as this is understood to be a 1 there, we could always use our distributive property to go ahead and distribute into the parentheses. So we could have said, okay, well, we could just go ahead and distribute this guy here. And if we distribute it, we have 2x cubed times 3x. That becomes what? 6x to the 4th, because 2 times 3 is 6. X to the 3rd times x to the 1. When you multiply them with the same base, you add the powers. And then we could distribute this over here as well too. So 2x cubed minus 5. 2 times 5, that's what? 10x cubed. 10x cubed. And then when we look here, we go ahead and say, well, now that we just distributed, because we really didn't take the derivative just yet. All we did was simplify the problem so that we can take advantage of one of our other rules. So now the derivative now, if we were to take the derivative of it, f prime of x, would be multiplying this here. So 6 times 4, that's 24, x cubed. And then 3 times 10, that's what? 30x squared. So this is the derivative of the function, and that is exactly the same as this. Of course, if we add the 6x cubed and the 18x cubed, those are like term because it's the same base to the same power. That gives you 24. 24x cubed minus 30x squared, which is the same thing as this. So what you will discover is that when you're given a particular function and you're asked to find the derivative of it, there may be more than one ways you can go about trying to find the derivative of it. You're learning all these rules so that you can find the rule that is most advantageous to you. So that's an example of the product rule. Alright, let's go ahead and show another example of the product rule. Okay, let's say, for instance, if we have 3x minus 2x squared times 5 plus 4x. And again, this is, let's say, f of x. We want to find f prime of x, the derivative. So f prime of x, always write out your rule. F prime of x is what? Derivative. Well, this is the product. We're going to first of all label this as your first and label this as your second. Label this as first, label that as second. So you're dealing with product. The idea is to break the function up into a product of two factors, or identify each of the two factors in the product that you're given. First step. Second step is to write out the rule, which is for the product, because we have a product situation here, it's first times derivative of second plus second times the derivative of the first. Okay, well, let's go ahead and identify each part. Now, the first is just the first function. So this would be what? 3x minus 2x squared. We're just writing it down. We're not taking the derivative with this f part of it. This part means we're taking the derivative of the second. So we identify what's the second and we take the derivative of that. So let's go ahead and say, okay, this is my second function here. If I take the derivative of that, well, I can use the sum and difference rule to say, okay, the derivative of this guy here is just 0. The derivative of this guy here is the derivative of 4x to the first power is just 4. So that's just 4 there. And then I have the second function, which is that function written out, 5 plus 4x times that by the derivative of the first. The derivative of the first, now, well, let's look. This is my first function. Again, I can use the sum and difference rule to take the derivative of each individual component here. This is my first. The derivative of this first term is 3. And then the derivative of this second term, multiplying these two together, that's 2 times 2, that's 4. Subtract 1 from the power, so it's 4x. And now I just want to clean up. I've already taken the derivative. I just want to clean up at this point. I need to distribute this 4 to each term in the binomial, so this becomes what? This becomes 4 times 3x, that's 12x. 4 times 2, that's 8x squared. And this now becomes, well, this is just a binomial times a binomial, so I want to use an operation that I got to FOIL this. First, outer, inner, last. So FOIL first, which is 5 times the 3. This is going to be, what, 15? Outer, 5 times minus 4x. That's going to give me a minus 20x. Inner, 4 times 3x. That's going to give me a 12x. And the last is 4x times 4x. That's going to give me a minus 16x squared. And then we just want to further clean up the problem by identifying or collecting our like terms and then simplify. Well, let's look at the x to the first power. And